So our goal now is to come up with this quote-unquote tangent parabola. In order for us to do that, let's take a quick look back at the point-slope form and the idea of the tangent line. All right, so we had this idea that the tangent line equation is written in this regard. I'm going to multiply, or rather morph this ever so slightly and just say we got this tangent line, so let me just going to call it, instead of y, I'm just going to call it t of x. All right, so t of x is equal to the function's value at a plus the derivative of the function's value at a times x minus a. All right, and why do we know this is true? Well, we know that this is true because the function has the, actually put it right over here. All right, the two have the same initial value, and they also have the same slope. All right, they have the same initial value because if I plug a into my tangent, all right, that means I'm going to replace all the x's with a, so I end up having f of a plus f prime of a times a minus a, which we know is 0, so this whole term wipes out, and we end up with t of a equals f of a. All right? And if I were to find t prime of x, well, I'm deriving this equation up here. The derivative of a constant is 0, and then I have f prime times the quantity x minus a. F prime of a, that's a coefficient, so that will become part of our derivative. And then I need to derive x minus a, and the derivative of x minus a is 1. So now if I plug a into my derivative of t, I end up with f prime of a as well. So whether it's our function, in this case the original function was natural log of x, or our tangent line, which, actually let me go back up, was right here, the natural log of 2 plus 1/2 x minus 2, right? Both of those equations had the same initial value and the same slope. Hence the reason why we had this picture on the screen, right? But now what we want to do is have more of a curvature to it. So if we want the same curvature as well, what is curvature connected to? Yeah, it's connected to the second derivative. All right, so we need to have the same second derivative. Okay, but more importantly, before we get the second derivative of t, we actually need t to be a parabola. All right, so if we think about a parabola, well, that means we need an x squared involved. So if we start to build it here, all right, t of x equals, well, we know that we have f of a for starters. That's our initial condition. And then f prime of a times x minus a, that takes care of the tangency. All right, but we also need a quadratic term, so we need x minus a squared as well. Well, if the first term had f of a and the second term had f prime of a, what do you think the coefficient of the third term might happen to be? Yeah, you probably just said to yourself f double prime of a. All right, well, let's see if you're correct. If this is correct, then t of x and f of x should have the same value at the second derivative. Now, we already know what t prime is equal to. It's right here. That's if we're deriving the initial term, our tangent line. But now we have a quadratic term here. So let's actually get t prime again. But this time we're going to derive our new function. We get, once again, this derives to 0. All right, we'll put that in. And then this will derive to f prime of a. And then this will derive to f double prime of a, and then we have to derive x minus a squared, so that's a little chain rule there, which says that we have to multiply the derivative of the outer function, so 2, and then we keep the inner function, x minus a, and then we multiply by the, now to the first power, and we multiply by the derivative of the inner function, which is just 1. So if we simplify this, t prime of x, well, the 0 doesn't need to be there. We have f prime of a plus 2 f double prime of a times x minus a, right? And if we were to plug in a for t prime, once again we would end up with f prime because x minus a, but a is equal to, x is equal to a, this whole term would go to 0, right? So now let's get our second derivative, t double prime of x. All right, well, f prime of a derives to 0. The 2 is a coefficient, so it stays. f double prime of a is a coefficient, so it stays. All right, and then x minus a derives to 1. So when we plug a into the second derivative, we have to replace all of our x's with a's, but there are no x's, so we're left with twice f double prime of a. And this is a problem because we want our second derivatives to be identical. But right now our second derivative is equal to twice, second derivative of t is equal to twice the second derivative of f. We need to get rid of that 2. In other words, we need to divide by 2, which means this needs to be divided by 2, which means this needs to be divided by 2, which means way up here, this needs to be divided by 2 as well. So what are we looking at? T of x is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. Right. Now, if we use this formula, we should get ourselves a tangent parabola. In the next video, we'll actually see that in action.